Hello everyone. So this is an extra video about chain rule. So recall that we know how to do chain rule. So this is the general chain rule. So basically, if your functions depend on so many variables, then you have to do those variable and do chain rule every time. So this is my general chain rule. So if it depends on x1, x2 to xn, so for if I want and x1 it depends on t1 to tm. So if I want to take partial derivative with t1, then we have to do x1 chain rule, x2 chain rule, and up to xn chain rule. So this is general chain rule. So this is good to memorize, and I think this is not too bad. But if you want to use the graphic way to do this, we also have the dependence chart. So if f is depends on x and y depend on s and t, so we just have to do this part and this part to do s. And we can also have something like this. So this is w is depend on x and y, and xy is depend on u and v, and u and v are depends on s and t, and v is depend on s. So if I want to take partial derivative with respect to s, we have to find how the path we go to s. So this is path 1, this is path 2, this is path 3, this is path 4. So this is 1, 2, 3, 4. And each layer, which is times this partial derivative, and partial derivative, partial derivative, partial derivative, and keep going, and keep going. So this is a good way to visualize how do we do chain rule in general. I think the chart thing is really good, really good. Please do know how to do this thing. Please do need to know how to do this thing. So now we do some application on chain rule. So basically, instead of just doing like the previous question like this, like taking derivative like on certain function, it's kind of boring. There are some actual application on chain rule. So some functions we have to do like in real life. For example, the first one is z if x, y, and now if I write x equals r cosine and y equals r sine. So you can note that in this expression, so x and y are in polar coordinate. So z will be a surface, and I want to rewrite that in polar coordinate. So I want to write an expression of zr and this z theta. So now we can see that z is depend on x and y are depends on theta. So z is depends on x and y depends on theta. So if I want to find r and theta, since r is also a function, r and theta. So if I want to find z partial derivative with r, so we have to go this path, this one, and this one. Okay? So again, if I want to go r, I have to do this one and this one. So we can happily write zr will just be partial z, partial x, times partial x, partial r. The second path is partial z, partial y, and partial z, partial y, partial r. That's it. So you do the exact same thing. So z theta. So choose a different color. So if I want to go to theta, this first path is this one. The second path is this one. So we can happily write this is zx, x theta, and plus zy, and y theta. So we don't know what z is actually is, so we can just leave that there, zx and zy. But we know how to do xr and xyr and x theta and y theta. Since we have x equals r cosine theta, so we have partial x, partial r will be now theta is a constant, so it will just be cosine theta, and partial x, partial theta. Now r is a constant. R is a constant, so it will be negative r sine theta. Okay? And y equals r sine theta. We do the exact same thing. So partial y, partial r will just be sine theta, and partial y, partial theta, will be r cosine theta. So with this, we can happily rewrite everything. So zr will just be I'll just write Zx times XR. XR will be cosine theta and plus Zy, and Zy or partial Y partial R will be sine theta. Will be sine theta. So similarly, we have Z theta. So Z theta will just be Zx partial x partial theta will be negative R sine theta and plus Zy, and Y theta will be R sine theta, R cosine theta. So this will be Zx cosine theta plus Zy sine theta, and this will be negative R Zx sine theta and plus R Zy cosine theta. So that's the answer. That's the answer. That's the answer. So basically just general. But in reality, we don't want to stop there. So maybe you have some questions that the function is given to you, the surface is given to you, but you want to rewrite that in terms of polar coordinate, or vice versa. If the question only gives you polar coordinate, and maybe the polar coordinate zr, z theta, I want to rewrite that in the regular things. So maybe in some questions, you write in terms of polar coordinate will be easier. So you can happily do the calculus on polar coordinates. So you will do zr, z theta, a lot of things, all using zr, z theta. But in reality, you might go back to the function zx and zy. So in reality, in application, maybe I don't say in real life, I say in application, we might be given zr, z theta, and we want to find zx and zy. So this is more like a transformation. So it's just like transformation. If you're in engineering department, you'll have to face like differential equation in the future. This is a really usual technique since a lot of things using the symmetry on circle on polar coordinate will be way more easier. So it's easy to do calculus on zr, z theta, but we want to transform back to zx and zy, or vice versa. So in this case, we are given two functions. I want to solve zx and zy. So we can solve that. So in this case, from zr, like zr equals zx cosine theta plus zy sine theta. I want to solve this. So basically now we want to rewrite everything in terms of zy and zx. So z theta will be negative r zx sine theta plus r zy cosine theta. I want to solve zx and zy. So maybe I write this. It'll be cosine theta zx plus sine theta zy equals zr. So basically, how I write this is that, okay, these are given thing. I want to solve this. This is my variable now. I want to solve this in terms of zr, z theta, and sine theta, cosine theta r. So similarly, we have this negative r sine theta zx and plus r cosine theta zy equals z theta. So again, these are my variables. So I want to solve what is zx and zy in terms of zr, z theta. So these are the usual things. How to solve this? We just try to eliminate things. So yeah, it's not easy to solve it, but we can try. For example, if I want to eliminate zy, so we have sine theta, r cosine. I want to get that away, so I just times them. I just times them. So we just do this. So the first equation, I times r cosine theta. So it'll be r cosine squared theta, zx, and plus r sine theta, cosine theta, zy equals r cosine theta ZR. So my goal is that I want to eliminate this guy. So I times r cosine theta on the first equation. So I need to times sine theta on the second. So this will be negative r sine squared theta zx and plus r sine theta cosine theta zy equals sine theta z theta. So we can happily cancel this out. So we just minus both equations. So we'll have this. The magic happens. So r cosine squared minus negative r sine squared. So it'll be r sine squared plus cosine squared of zx. And this goes away, plus 0, equals r cosine theta zr and minus sine theta z theta. So we know that sine theta plus cosine theta is 1. So this is 1. So finally, we'll have this. Rzx equals r cosine theta zr minus sine theta z theta. So we can happily get our zx. So zx will just be cosine theta zr and minus sine theta over r z theta. Yay! So we have this. So we do the exact same procedure to eliminate z theta, to eliminate zx. So I'll skip that, but basically follow the same thing. Similarly, we'll have the same thing, like zy. So it'll be zy xy will just be, I'll skip this, but I think you know how to do this. Basically, the first equation I times r sine theta, and the second one I times cosine theta, and I add them up together. If again, we will have like sine squared plus cosine squared. So zy will be r times zy, and the left one zx will disappear. So yeah, you can see how it goes. So it will be sine theta r and plus, since in the previous case we have to minus, but now we have to add them together. Since -1, the second one is negative, the first one is positive. So I think you can guess it. It will be cosine theta over r z theta. That's it. So in real life or in application, you'll see this a lot. We do the transformation from zx zy to zr d theta. So by chain rule, we can have that, or we can do vice versa. If you're given zr z theta, you can have zx z. Okay, so this is my first question. The second one, this is basically just, I'm not hiding. We have to do something like differential equation. So again, maybe I change a little bit. So I changed it to not uxy, I changed to uxt. So basically, you can see that this is like a spatial and temporal thing. So a function defines on x and defines on like given x and given t. So at some place and at some time. And if the function looks like this, no matter what f is, it will always satisfy this partial differential equation, utt equals c squared uxx. So in this case, basically, we just have to check it. We only have to check if that's the solution. We only have to check that, okay? Satisfy just means that we have to check big utt equals c squared big uxx. And that's it. So we just do the differentiation on this function. So don't worry about this one, even though we only learned chain rule on first derivative, but basically we can do the exact same thing on second derivative. So we just do derivative first time, and then we do second derivative. Okay. So I introduced this problem, just I want to show you this problem. You face question like function right like this. So if you write something, this is uxt equals fx plus ct and plus gx minus ct. So basically, x plus ct is your input right now. So you can rewrite f in terms of like this. So you can write fx plus ct. It means that f, and you have a function inside, maybe small u of t, and where u of t is x plus ct. Okay? Sorry, u of x, sorry. It's a two variable function, so uxt, and u of xt is x plus ct. Okay? So it's also a layered function. It's just equal right in this way. So in this case, we can see that f is in terms of u, and u is in terms of x and c. So now we have this. This is my f, and f is depend on u, and u depends on x and t. Okay? So we can write the flow, we can write the dependence chart like this. Dependence chart like this. So if I want to find u and x, we just follow the same thing. So if I want to find, okay. First of all, if uxt, I want to find ut, it would just be f prime t, the partial f plot, partial t plus partial g partial t. So first of all, maybe I'll write this. This is still valid. And first of all, we can write ut. The goal is to want to find ut. It's basically partial f partial t and plus partial g partial t by the linearity of differentiation. So we do two part. And similarly, ux will be fx, maybe partial f partial x, and plus partial g partial x by linearity. So we're just doing two times. So now I have this. So partial f partial x, we have to follow this path. So this will be partial f partial u times partial u partial x. Similarly, partial f partial t will be follow this path. Will be partial f partial u partial u partial t. That's it. You don't have to do fancy trick. We just draw out a dependence chart. Everything is clear. Okay. So we'll keep the partial f partial u since we don't know what is that. We just keep that. So this will be fu, but we know what is u. So u is this guy. X plus ct. So partial u partial x is just 1. Okay. So similarly to partial f partial t, so we keep the partial f partial u, and partial u partial t is now c. So basically chain rule. So we have this. So now we want to do the exact same thing with f with double derivative. So if we already know that partial f partial x is fu, so this is fu, and this is cfu. So partial, if I want a second derivative, partial square f partial x squared. So this will just be I taking partial derivative of partial f partial x. So this is just partial x. This is fu. So it's just partial fu partial x. So again, the same thing. After you take derivative, it still depends on the same thing. So the dependence chart is exactly the same thing. It's just the function become fu. So we follow the exact same thing. So this will just be partial fu, partial u, and partial u, partial x. Is that okay? Oh, sorry, this is a video. So yeah, I hope this is okay. So dependence chart doesn't change when you take derivative. If it depends on the things, you depends on the same thing after you take derivative. So partial u, partial x still 1. So in this case, this is fuu, taking second derivative. So we do the same thing. So, oh, I need more pages. We do the exact same thing. So now we have partial square, partial t, partial t squared, partial t squared. It is partial t, like ft. And we already have ft is cfu. So partial t, cfu. We can happily take out c. So it's partial fu, partial t. So partial ft, partial fu, partial t is exact same thing. So basically, using the same dependence chart, so we can happily write c times partial fu, partial u, and partial u, partial t. So this will be c times f uu times, we have it above, so c, so it'll be c. So this will be c squared fuu. That's it. That's it. So c squared fuu. C squared fuu. So we have it. We have it. So this is part of f, and now we have to do the part of g. So we do the exact same thing. So g is x minus ct. So we can write g of maybe a function called v of xt, where v xt is x minus ct. So the dependence chart of this one will be g depends on v, and this depends on x and t. So we do the exact same thing. It's just different function v. So g partial x will be partial g partial v and partial v partial x. We do the exact same thing. We do the exact same thing. So in this case, partial g partial t will be partial g partial v partial v partial t. And partial v partial x is still 1, and partial v partial t will be negative c. So in this case, we can happily write this is gv times 1, and this is negative c gv. So the second derivative, the dependence chart of gv will still be the same thing, exact same thing, exact same thing. So I'll just keep it faster. You can, of course, slow the video down or pause it or try yourself, but I think this is straightforward. So the double derivative, so partial g, partial square g, partial x squared. So this will just be this guy. Partial will be gx. So will be partial x gv. So in this case, this will be the same dependence chart. So it will be partial gv, partial v times partial v partial x. So in this case, this is gvv. And for partial square, partial g, partial t squared will be partial t gt. So we do have it. So this is partial t, negative c gv. So this will be negative c and partial gv, partial v and partial v, partial t. And this one is negative c, and negative c times negative c will be c squared. So this is c squared gv. And that's it. So we have f part and g part. We just add them together. So we have utt xt will just be like ftt plus gtt. So ftt above is c squared fuu, c squared fuu, and gtt is above is c squared gvv. And xx xt will be fxx plus gxx. So fxx, we see that above, will be fuu. This is fxx, this is fuu, and this is gxx, this is gvv. So this is fuu plus gvv. So this guy is c squared fuu plus gvv. So we can happily have it. So this is UTT equals C squared, big U, UTT, big UTT equals C squared UXX. So we can happily say that UXT satisfy a function UTT equals C squared UXX. This is a really beautiful result. So if you're interested, this is called the wave function. This is called the wave function. Wave equation, sorry, wave equation. So basically, it's just you have to satisfy the thing, then it will be a wave. It will be a wave. So this solution is like two wave. The solution of wave equation, it will be like wave. So if you, I think it will be the second course of partial differential equation. You will learn about this. So you can see that this is basically two traveling wave. One is traveling this side, one is traveling this side. If you have something like, if you remember in physics, you have x naught plus vt is your, if you have an equi-speed motion, it's the position you'll move to. So this means that, okay, your move f will follow this kind of thing, x plus ct, and g will follow this, x minus ct. So if they put together, you'll be satisfying the wave equation. So this is beautiful. This is beautiful, and even have an m. So this solution we call the Lambert solutions. The Lambert. I hope I spelled correctly. Solution. So this is a really beautiful solution. This is a really beautiful solution to the wave equation. But we don't have to know. You don't have to know how to derive it right now. But at least by the chain rule, we can verify this is the actual. This is the actual solution. So this is pretty. This is pretty. Maybe you think, okay, this application sounds boring. So, okay, we just verify something is a solution. We cannot find a solution. And the previous case is also, okay, similar to differential equation. And we just do some transformation. But actually, we can do some actual application problem like this one. Oh, I already typed it. So a radius of the right circular cone is increasing at 3 inches per second. And the height is decreasing at 2 inches per second. And what is the rate of changes? So basically, I want to find volume of the thing, and the radius and the height are both changing. So it's just not, it's not like it's different from the previous case, the linear approximation. Now we have two things that's moving. Two things are moving. So basically, this is the circular, maybe not cone, circular cylinder. I'll change to circular cylinder. So cone is different thing. But if you remember, cone is 1/3 of the cylinder, but I'll change that. I'll change that. So this is my cylinder. So this is my radius. This is my height. So volume, maybe I write it V. It depends on R and H. Depends on R and H. And this case will be pi R squared H. So now R is a function of t, H is a function of t, since they're increasing per second, decreasing per second. And now R is a function of t, H is also a function of t. So now it's time for using chain rule. Yay. So we know that the goal is to find that dv, we want to find partial v, partial t. This is my goal. This is my goal. I want to find partial v, partial t. Or you can just write dv dt, since you can rewrite as a single variable function. It doesn't matter. And we know that the rate of change of the radius, so partial r, partial t, it is 3, increasing, so positive. Sorry. And partial h, partial t, since it's a one variable function, so we can happily write this as dr dt is 3, and partial h, partial t is dh dt. It is decreasing, so it's -2. And in order to find the volume of the cone of cylinder, I'll change to cylinder. Changing when the height is 20 and radius is 40. So basically, I want to find this guy. at R equals 20, R equals 14, and H equals 20. So that's it. So I translate the wordy problem in terms of mathy problem. So V is a function of I and H are function of T, and I want to find this. So we can happily write our dependence chart. So this is my V. It depends on R and H, and I and H are all depends on T. And I want to find what is dV dt. So there are two paths, one path, two paths. So partial V, so dV dt, it's just partial V, partial T, will be partial V, partial R, partial R, partial T, the first path. Second path, partial V, partial H, partial H, partial T. So we write everything in terms of one variable. So it'll just be partial V, partial R, dr, dt, and plus partial V, partial H, and dH, dt. That's it. So that's it. That's it. That's what we want to find. 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 So we can do the calculations. We can do the calculation. So so partial V, partial R, it's just a regular partial derivative, right? So partial V, partial R, record that V H, it is pi R squared H. So this term, partial V, partial R, is just partial derivative. So it'll be 2 pi RH. And similarly to partial V, partial H, every other things, they are just constant. So it would just be pi R squared. Okay? And dr dt is already given. dH dt is already given. So we can happily write this down. So dV dt will just be dV dr is 2 pi RH and dr dt, and plus pi R squared dH dt. So we plug in number is 2 pi R is what? 14, and H is 20, and dr dt is 3, and plus pi R squared is 14 squared, and times -2. I'll leave it here. So it's just calculation. I'll leave that to you. And that's it. And that's it. And that's it. So this is some actual application problem. So that's all for the example. That's all for the example.